Coordination compounds. We talked in, what chapter was that? We talked in one of the earlier chapters about complex ions, right? How copper forms a complex ion with ammonia molecules. And it's the transition metals that tend to form these complex ions. A complex ion contains a central metal ion that's bound to one or more ligands. The ligands are Lewis bases, meaning they're electron donors, and they will form a bond with the metal ion. So what's a coordination compound? It's just the compound including the complex ion. You can't have complex ions by themselves. There has to be a counter ion. So the coordination compound is the neutral compound consisting of a complex ion and one or more counter ions.
Is that like where you have a complex ion that's like hydrated? Like the water is the...
No, it's like, well, like here, this is a complex ion, right? And it's got a 3+ charge. And so in the compound, you're going to have counter ions that balance it. So here it would have 3 chloride ions that balance the positive 3 charge on the complex ion.
That's not what the water does when you have that complex ion.
Well, water forms hydrates with substances, but that's not counteracting charge. And water forms ion dipole interactions with ions in solution, and that's making it more comfortable, but that's going to go away if you evaporate the water.
Yeah.
Right? So there has to be a counter ion. Kind of.
It's like we don't have anything better, so we'll use water because he's always here and he's so nice to me. So
Yeah.
I'll choose him right now.
Yeah, if I'm feeling positive, he'll be the negative for me. If I'm negative, he'll be the positive, right? He could just go either way. So there are 2 types of interactions that the metal has in these coordination compounds. One is called the primary valence. That's the oxidation state on the central metal ion. And then there's the secondary valence, also called the coordination number, which is a lot more descriptive. And that's the number of molecules or ions that are directly bound to the metal. So if we look at this coordination compound, the whole thing here is the compound. Over here, this part is the complex ion. These are just counter ions. So we have cobalt in here, and it's got 6 ammonia molecules around it. What is the oxidation state for the cobalt? What's the charge on the cobalt ion? Well, do these ammonium molecules have charges? Yeah. NH3, does that have a charge? No.
No, it doesn't.
Doesn't. These are neutral molecules. They're Lewis bases. Yeah. They're donating electron pairs. Right? So with neutral molecules, the charge on the complex ion is the same as the charge on the metal ion. Yeah, with neutral molecules it is. If it's got ligands that are ions, then it's not the same. So the primary valence here is +3. That's the charge on the oxidation state on the central metal ion. What's the secondary valence for this one? 6, because there are 6 molecules or ions bound directly. It's the number of ligands. Okay, so that's a coordination compound. And we see over here its formula. The complex ion is in brackets. We've got the cobalt, and then this is the ligand, and on the outside, the parentheses, the number 6 tells us how many of those. And then this is the counter ion. So here are 2 other coordination compounds. So let's draw those in here, just because we can. So, ooh, isn't that fun? What if we stuck chlorine in there? So that would be this guy. Cobalt, NH3, 5, and now chlorine is also one of the ligands. That changes, well, I don't need to do that. I can just do that. That changes the charge to 2 plus, right? And then we don't need both of these. I mean, all three of those, we only need 2. So the chloride can take the place of one of the ammonia molecules as a ligand.
But it won't knock it out of place.
It's a different compound. It's just a different compound. And so this guy down here, CONH3,4Cl2, now we're going to get rid of another one of these and replace it with chlorine.
Why that?
Because I just picked it. There's no reason. And then what's the charge on this complex ion now? +1. And then we don't need this guy. So the counter ion, just like, back the real basic nomenclature that we talked about, why is sodium chloride NaCl? Because the sodium has a +1 charge, the chloride has a -1 charge. We put them together in the lowest ratio that the charges add up to 0. So when this has a positive charge, because this is a chloride ion in here, and that's balancing the charge on the cobalt, then we only need 1 chloride on the outside as the counter ion. Any questions?
Does the molecular geometry change as you replace the ammonias with chlorides?
Does the molecular geometry change when we swap in the chlorides for the ammonia? It gets more interesting, and we're going to talk about that. We're going to talk about, we have a possibility now for isomers that was not there before. We'll talk about that. But it's probably, this is, do you know what the shape of that thing is? Octahedral. It's still going to be roughly octahedral. Any other questions?
And electron chemistry isn't really lying. All of it is probabilities. It's not hot. It's just like, it's kind of like that.
So the bond between the ligand and the metal is called a coordinate covalent bond. And what happens is the ligand is donating a pair of electrons to an empty orbital on the metal. So here we have our silver ion. It has some empty orbitals, right? Some empty d orbitals. And here we've got Lewis base, 2 ammonia molecules. Each of these has a lone pair. So if we let this lone pair overlap with an empty orbital on the silver, it can form a bond. It's called a coordinate covalent bond. It's not ionic. There's a sharing of electrons, but both of the electrons that are being shared come from one part. They come from the nitrogen. So nitrogen's being very generous, right? Here are some other common ligands. Water. Water has 2 lone pairs on the oxygen. It can form a coordinate covalent bond. Ammonia, chloride ion. The ion has a noble gas electron configuration. It's got 4 lone pairs. It can share a lone pair with the metal ion and form a coordinate covalent bond. And so as you look at all of these, what they all have in common is some lone pairs. They're Lewis bases. They can donate an electron pair. Any questions? The one on the bottom is ethylene diamine tetraacetate, EDTA. Yeah, it's a little bit small. It'll show up a little bigger in another slide. And so the charge on this complex ion, because these are 2 neutral molecules, the charge on the ion is the same as the charge on the metal ion, right? It's sharing electrons with the silver ion, but the charge is still there. Overall, it's still short 1 electron. If you've got chloride, though, sharing, then the charge would be different because the chloride is an ion. And some of these are ions and some of them are molecules. There are different kinds of ligands, monodentate, bidentate, polydentate. And this has to do with how many pairs of electrons do they donate. How many coordinate covalent bonds does one ligand form with the metal ion? So monodentate forms only one bond, donates one pair of electrons. A bidentate ligand donates two pairs of electrons. Each pair of electrons comes from a different atom. Okay, so here is ethylene diamine. And it is bidentate because this nitrogen can share a lone pair with the metal ion, and the nitrogen at the other end can also share. All of these single bonds have rotation, and so this guy can bend around, and the nitrogen on one end hooks up, and the nitrogen on the other hooks up. Yeah, cool, huh? So the two common bidentate ligands are oxalate and ethylene diamine. Oxalate's abbreviated OX, and ethylene diamine is abbreviated EN. Don't ask me why, just because. Polydentate have more than two, more pairs of electrons. And so here's our friend that you were asking about, ethylene diamine tetraacetate ion. EDTA, it's got a 4- charge. This is the most common polydentate ligand. And here's a picture of it. So EDTA wraps itself completely around the metal, and it can donate up to 6 electron pairs. So here we see the structure of this molecule, and we can get a pair of electrons from each of these oxygen atoms out here, and also from the 2 nitrogens in here. So this illustration here is showing a cobalt ion with 3 ethylene diamine molecules. So there's the nitrogen and nitrogen of 1. So it's, looping around. It's like, I don't know, holding hands, 2 hands grabbing onto it. And here's another one over here and another one up here. This is cobalt with 1 molecule of EDTA. And it wraps itself around and forms 6 coordinate covalent bonds with the cobalt. That's why it makes such a good chelate. A chelate is a complex ion that contains a bidentate or polydentate ligand, and that ligand is called a chelating agent. And EDTA is an awesome chelating agent. If you want to get ions, metal ions, most specifically transition metal ions, out of your solution, you throw EDTA in there, and it will just surround them and take them out of circulation, in essence. It keeps them busy, and so they're not going to react with other things. Chelating agent.
Helps them get into plants.
Yeah, helps them get into plants, keeps them from, forming rust or, doing these other things or precipitating out. So, very useful. The coordination numbers, which is also called the secondary valence, coordination numbers vary from 2 to 12. 4 and 6 are the most common, though. So you commonly see 4 to 6 coordinate covalent bonds. 2 is the smallest. If you have 1, it's just probably going to be an ionic compound, right? It's not really going to be a coordination compound. So if we have 2, that's going to happen with the +1 ions only. For the first row transition metals, you're mostly going to see 6 or below, and those are the ones we're going to talk about the most. There are compounds with odd coordination numbers, but those are really rare, so we're going to ignore them. The geometry of the complex ions is going to depend on the coordination number, but it can also depend on the number of d electrons in the metal ion. And so these are the 4 most common situations. If you have a coordination number of 2, you're going to get a linear shape, where you have the metal ion in the middle and 1 ligand on each side. For 4, like I said, the 3 is very rare. We're going to ignore it. For 4, you can either get a square planar geometry or a tetrahedral geometry. And that's going to depend on the number of d electrons. to get this, you need to have another d orbital up and down. It's more like the octahedral, but missing the top and bottom. Tetrahedral, we're familiar with that shape from the geometry of carbon and all kinds of other things. If you've got a coordination number of 6, you're going to get an octahedral geometry. And these guys are examples of those. Any questions?
Oh, I do.
Okay.
When you said that 2 occurs with 1 plus ions, what does that mean?
It means like with something like iron 3, you're not going to see a coordination number of 2. You'll probably see 4 or 6. And so the example here is silver with 2 ammonia molecules. Silver has a +1 charge.
Okay.
So 2 is not as common. It does occur, but it's not as common. And you mostly see it just with the +1 ions. And there's a number of +1 ions. Any other questions?